All right, our next speaker this morning is going to be Beryl Hovis-Afflerbach, who comes to us from Caltech, where she is a rising junior. Beryl has been working this summer with ILVA, and she'll tell us about her project, Are High Mass Stripped Stars Missing in the Small Magellanic Cloud? Go ahead whenever you're ready.
Thanks. Hi, everyone. Thank you, Gwen, for the introduction, and thank you, everyone, for coming today. As Gwen said, I've been investigating stripped stars. A stripped star is created when a high mass star in a binary swells, overfilling its Roche lobe, and its outer material is stripped by its binary companion, leaving behind a stripped star. Stripped stars are expected to be the most common type of binary product, with about 30% of massive stars becoming stripped at some point in their lifetimes. They're also, as the hot, bright helium cores of their progenitors, they're expected to be very easy to identify observationally, but very few have been observed. So why is that? We're investigating specifically if we expect stripped stars to be missing in low metallicity environments. Since radial expansion is crucial to the creation of a stripped star, we investigate how the radius of a star changes over the course of its life. This Hertzsprung-Russell diagram, showing the luminosity and the temperature over a star's life as it evolves, is one that we've made for 27 solar mass stars at solar metallicity and at metallicity similar to that of the Small Magellanic Cloud, which is lower than solar metallicity. Both stars spend about 90% of their lifetimes on the main sequence, but it's when they evolve off the main sequence that their evolution starts to differ. The solar metallicity star expands significantly to more than 1,000 solar radii before it begins burning helium in its core, when about 10% of its lifetime still remains. And in a binary, that star would become stripped at that point, creating a long-lived stripped star, since the helium burning phase is a long-lived one. However, the low metallicity star does not expand past 60 solar radii at that point, and doesn't expand significantly, and therefore wouldn't become stripped until much later, once the helium in its core has been depleted and it's much closer to core collapse. Therefore, it would not be able to create a long-lived stripped star. And since the observational frequency of the stripped star phase is based on the intrinsic frequency of the phase, as well as the length of the phase, if the star does not become stripped until very late and can't create a long-lived stripped star, we would expect to observe many fewer. So now we want to know what the range of initial stellar masses within which we expect this to occur is. To do that, we use a one-dimensional stellar evolution code, which, to model a star that might look something like this, take something that looks like this, just one-dimensional code from showing the radius of the star. And it solves the 4 equations of stellar structure, assuming that the star has spherical geometry. And from that, it outputs general stellar properties as a function of time, and as well as the interior structure of the star as a function of time. So we can define things like the core. From this, we determine what the radius of each star is for a range of initial masses from 2 to 100 solar masses at the time of helium ignition, when approximately 10% of the star's lifetime remains. And we find that at lower metallicity, at SMC metallicity, the stars between about 20 to 50 solar masses don't expand past about 100 solar radii at that point, while below and above that mass range, as well as at solar metallicity, they expand to around 1,000 solar radii, an order of magnitude higher. Therefore, we expect stripped stars to be very rare in the SMC, but in this mass range. The next question we ask is this theoretical prediction observationally testable? And to determine this, we want to use observations from our collaborators, Bethany Ludwig and Maria Trout, who are working on identifying strip star candidates in the Magellanic Clouds. This is a color magnitude diagram showing observations of stars in the Magellanic Cloud, in the small Magellanic Cloud, with their brightness as well as their UV color. And strip stars are expected to be very UV bright, so we expect them to lie to the left, bluewards, of the 0H main sequence. These models of strip stars reaching up to 7 solar masses lie in that area. And there are also observations of strip stars, the candidates that they've identified, which have been observed with the spectrograph and are consistent with expectations for binary strip stars. There's additionally, there are observations of higher mass Wolf-Rayet stars, which are self-stripped due to strong stellar winds. So now we want to know, where is it on this color magnitude diagram that we expect strip stars to be missing? The mass range we identified is about 20 to 50 solar masses. And since strip stars should have a mass equal to that of the helium cores of their progenitors, we would expect the strip star masses to be between about 7 and 22 solar masses. So we extrapolate from these strip star models to get magnitudes that tell us that this is approximately where we expect these strip stars to be missing. And this theoretical prediction is observationally testable. And to do this numerically, we want to figure out if long-lived strip stars are in fact created in this area, if those stars do swell early on, creating long-lived strip stars, how many strip stars do we expect to observe here? And if we observe significantly fewer, then that would support our prediction that strip stars are missing here. So to do this, we solve this equation. We integrate in the mass range within which we expect stars to remain small. We use the star formation rate, initial mass function, the lifetime of a star, the fraction of stars which get stripped, and the fraction of a star's lifetime which it is expected to spend in the helium burning phase. And this tells us that we expect about 50 strip stars to be in that area of the color magnitude diagram, or to exist if strip stars are in fact not missing. But there's an issue with this, which is that when the star becomes stripped, the companion accretes all of that lost mass, becoming in many cases very bright, and frequently bright enough to obscure the strip star and make it such that we cannot observe that strip star. So we don't actually know what fraction of strip stars should be visible. Initially, we say, well, it's between 10 and 100%, which is a pretty wide range. So what we're doing right now is running stellar population models to better constrain that. And how these stellar population models work is they convolve the results from the stellar evolution models with measured distributions from observed stars, such as the binary fraction. So currently, just assuming that the more massive star will be the one which dominates the observation and which will be visible, we're thinking that this fraction of stars that are of strip stars that should be visible is probably closer to 10%. So not very many. Another thing that we've done with these stellar population models is altered the code such that the Hertzsprung gap phase is defined as ending when the star becomes a red supergiant. So essentially what we're doing there is assuming that stars do swell before starting helium burning, and therefore long-lived strip stars will be created, counter to our theoretical prediction. And if we do this, this is the approximate mass distribution that we get. if we don't alter the code to make that assumption, we find that the mass distribution outside of the identified mass range is about equal, but within that mass range that we've identified where we expect strip stars to be missing, almost like about half as many are created as would be created if we assume that all stars swell before helium ignition. So in summary, our models predict that in the small Magellanic Cloud, stars with initial stellar masses between 20 and 50 solar masses will not expand until very late in their evolution, and therefore will not create long-lived strip stars. And therefore we expect strip stars with masses between 7 and 22 solar masses to be missing or very rare in the small Magellanic Cloud. And this prediction is observationally testable using data from the small Magellanic Cloud. What we want to continue doing is trying to constrain our numerical prediction using the stellar population models. We also want to improve our estimate of where we expect stars to be missing in the color magnitude diagram by, instead of just extrapolating from those lower mass strip star models, interpolating between those models and the higher mass Wolf-Rayet stars. We also want to compare with other regions of the color magnitude diagram and see if in those regions if the number of strip stars observed there lines up with predictions, with what is predicted. And of course, compare the theoretical prediction with observations, which leads us to the final question for the future: do observations of stars in the small Magellanic Cloud support this theoretical prediction? Thank you, and can I take any questions?
Nice job, Beryl. Questions for Beryl?
I do have like a question here. It's a great work. But why do you look into SMC but not like the Milky Way? So I understand that you are looking at MOH of -3, but of course in the Milky Way it's not hard to find things that are like -2, and there are a lot of like OB spectra. There are lots of interest in strip star just because of LB1. So have you looked into like the Gaia data? With like Lamos, of course, like with SDSS5, there are lots of interest in the OB star. Seems like there are lots of potential here.
Yeah, so we've been primarily focusing on the small Magellanic Cloud in large part because this project is largely motivated by the work that Bethany and Maria are doing right now, identifying the strip star candidates in the Magellanic Clouds using optical and UV data. So it's designed to be tested using that data, but we also definitely in the future could look into different environments. Thank you for the question.
Other questions for Beryl? All right, go ahead, Lauren.
Great talk. You mentioned that the stars might be missing because their companion could be outshining them.
Mm-hmm.
Do you know, are there any other observational things that might cause the stars to be missing other than physics?
Yeah, I mean, there are definitely, or to be missing or to like alter how we need to look at the
well, you just like, you're looking to see whether these stars are missing due to the physics, but I'm wondering if there are other observational things that might cause them to be missing.
Yeah, so I think one other thing that
Sorry, do you want me to rephrase
sorry.
the question? Is it not making sense?
No, I think it does. I think we're mostly looking into like this possibility. We haven't talked a lot about other reasons why they could be missing. I don't know if that answers your question.
No, that's good.
Okay.
Any other questions for Beryl?
I think I have one. This is Andy. It might be a dumb question. So you can make Wolf-Rayet stars, as you pointed out, by stellar winds, but also by stripping, by mass transfer, as you have for your stripping. Does this alter the Wolf-Rayet star frequency or the subtypes? Because there's WN and WC types, and would you expect to see a different ratio of the subtypes of Wolf-Rayet stars, or even Wolf-Rayets to main sequence stars that would be a test of your modeling?
I'm not sure how this would affect the frequency of Wolf-Rayet stars. One thing that we did note is that these 4 observed Wolf-Rayet stars do fall in this this range where we expect strip stars to be missing. So we want to ensure that we're like differentiating between those when we look at the observations.
All right, very nice job, Beryl. And let's go ahead and move on to the next speaker when we have a chance. Thank you.
Thank you, everyone.